a formula. Lynn, why didn't you just tell us this? Well, I already explained why I didn't tell you this. But this is called a computational formula. What that means is that this calculation here, which says take the standard deviation of your population and divide by the square root of your sample size. All right, this formula calculates SEM. This formula will give you the standard deviation of your sampling distribution of means. But do you understand why? I sure as heck don't. I have no clue why this gives you this. All right, I don't understand how anybody figured this out. I mean, obviously, it just couldn't have been by accident. Like, there's got to be some logical reason here, but, kind of damned if I know. I have no clue. All right, but this formula will give you SEM. And you don't have to exhaustively sample because all you need is the standard deviation in the population. Notice how I said all you need is this. Do you see a problem? How are we going to get that? Right? So this is the standard deviation of the population. All right? And the answer is going to be here, by the way, why it's stupid. But let's just go through this formula. So just to make sure, this is the standard deviation of the population. N is the size of your sample. So if you have 10 scores, 20 scores, 50 scores, whatever. Once you perform this calculation, you're getting SEM. You're getting the standard deviation of the sampling distribution of means. And it tells you, on average, how well X bar estimates mu, on average. All right. So are your X bars on average close to mu, or are they far away from mu? All you have to do is this. But again, there's a problem. How often do we know the standard deviation of the population? Right? Remember, 9.9999 times out of 100, we don't have access to the entire population. So we don't know what the standard deviation is. And if we did know the standard deviation, that means we know the parameters of the population. That means we also know mu. All right, so you see how it's kind of like method number 1. All right, we can't calculate standard deviation of the population because we don't know it. And if we did know this, well, we would know mu. So why are we doing this to begin with? You see how it just doesn't make any sense? So are we stuck then? Do we simply give up? Of course not. We're going to move on to method number 4. But before I do that, I want you to think about something. When we don't know mu, we estimate it, right? We estimate it with X bar. That's what we do. When we don't know variance of the population, sigma squared, when we don't know sigma squared, what do? We estimate it with S squared. When we don't know sigma, what do? We estimate sigma using S. So when we don't know sigma sub X bar, what do? Well, we estimate it using S sub X bar. See how easy that is? We just estimate it. Now, once we do this calculation, I'm going to show you that in a second. Technically, this is not standard error of the mean. Technically, this is an estimate of standard error of the mean. Okay, this is SEM. This is the estimate of SEM. Now, if I ever ask you that in a quiz question, I will say, is this SEM or is it an estimate of SEM? And you're going to say it's an estimate. But when in lectures and even in the book, After I point that out, I drop the fact that it's an estimate. I just refer to it as SEM because it would get tedious to keep saying over and over again, well, this is just an estimate of SEM. All right, I just want to point that out. Okay, so how are we going to calculate this? It's just a quick little change to the formula. So instead of sigma sub x bar, right, instead of this, we're going to put S sub x bar. Remember, this was sigma? Well, now it's estimated using S. Instead of putting the standard deviation of the population here, we're going to put standard deviation of the sample. And sample size does not change. All right, so can you calculate this? Absolutely 100% of the time. You have your sample. It's a quick and dirty calculation to get the standard deviation. We'll let SPSS do that for us. All right, but we can easily get the standard deviation. And with a little bit of math know-how, we can take the square root of the sample size and then finally divide S over the square root of N. All right, and so we can easily get this calculation. So this is what we're going to use as our estimate of SEM. It is an estimate of sampling error, an estimate of sampling error. All right, let's see now. So we can calculate this SEM, right? S sub x bar. And when we calculate it, it's telling us how much sampling error we have attached to the mean of our sample. Okay, so we get an X bar from our sample, we get a sample mean. We want to know, well, on average, do we have a lot of sampling error, a little bit of sampling error? Because if this number here is big, that means that on average, our X bar is probably going to be far from the mean if this is big. And if this is a small number, that means that our X bar that we just calculated is probably a good estimate. So you see how the size of this tells us how much sampling error we have, and it tells us how accurate our particular X bar probably is. Okay, so if this is big, X bar is probably not a very accurate estimate. If this is small, X bar probably is a good or accurate estimate of mu. Right? Now, sometimes when you are reading maybe an article or, I don't know, maybe sometimes in my book, I might refer to just standard error or SPSS. A lot of times SPSS just talks about standard error. And almost always when somebody talks about standard error, they're talking about standard error of the mean. In other words, they're talking about this, SEM, standard error of the mean. And they just, we get a little sloppy and we just say, people know, and we leave out the M, okay? But just so you know, when people talk about standard error, it's almost always standard error of the mean.